Okay, so welcome everyone to a new series of Quantum Spain seminar. Today we have Diego García-Martín from Los Alamos National Laboratory. Diego studied actually biology in University Autónoma of Madrid, but then he loved physics more, I guess, and he moved to La Laguna to study physics, a physics degree, and then he came back to Madrid to the Institute of Theoretical Physics in Autónoma University to study a master in theoretical physics. And then he decided to pursue a PhD in quantum information sciences and especially quantum computing between Germán Sierra group at Autónoma University of Madrid and our group at BSc and also University of Barcelona with José Ignacio Latorre. And then after his PhD, he moved to Los Alamos National Laboratory in the United States to do his first postdoc. And today he will present one of his recent results on showcasing Barren Plateau theory beyond the dynamical algebra. So thank you very much, Diego, and the floor is yours.
Thank you very much, Alba, and thank you for inviting me and having me here today. So today I will present our recent work showcasing a Barren Plateau theory beyond the dynamical algebra. So here is the outline of what I want to tell you about today. So as you may imagine, there's going to be a lot of Barren Plateaus. So first I will review the concept of Barren Plateaus and why it is a problem and a challenge in quantum machine learning. Then I will review the known sources of Barren Plateau, or at least what we knew, like say 3 months ago about what can cause a Barren Plateau. Then very recently, a couple of papers introduced this unified theory of Barren Plateaus, where they were able to unify all these different scatter results in one framework. But we'll see that they still require one assumption, which is basically that either the measurement operator or the initial state lies in the dynamical algebra of the circuit. So now, and finally, I will present our recent work where we go beyond this assumption and we present a complete characterization of Barren Plateaus for certain parameterized quantum circuits. Okay, so let's get started. What are Barren Plateaus? Okay, we are here. We'll be talking about variational quantum algorithms in the context of quantum machine learning. So I guess the audience is familiarized with this, but I'll just briefly review it. So these algorithms have become very popular in recent years in the literature. So they are hybrid algorithms. So we'll have a quantum computer and a classical computer working in tandem. So the role of the quantum computer is gonna be prepare a trial quantum state. Where is it? Okay, never mind. So it will prepare a quantum state using a parameterized quantum circuit. So these circuits can have gates with parameters that we can tweak in order to modify the state that we are preparing. So for instance, you can think of single qubit rotations with some angles. And once this quantum state has been prepared, we are gonna measure some observables. We are gonna post-process them in order to compute a loss function. And then we are gonna feed this loss function value to a classical optimizer, which can be gradient based or gradient free or whatever. And then we're gonna go on this optimization loop where the classical computer will propose a new set of parameters, we prepare a new trial state, and we will try to minimize the loss function. And here I'm gonna be focusing on loss functions of the form written there. So we'll have our quantum state rho. We are gonna evolve it with our quantum circuit U, which depends on variational parameters theta, and then we are gonna measure some Hermitian observable O with bounded norm. Okay, so why have these algorithms become so popular in recent years? My take on this is that on one hand, okay, we have seen the success of classical neural networks. So it's impressive what we can do now with them, ChatGPT, AlphaFold, etc. So Okay, I guess this has generated a lot of expectation as to what to expect with quantum computers, whether they can, provide some benefits for this type of applications. And then also it's a very flexible paradigm, so it's very easy to fit problems here to the quantum algorithm because you just have to encode it as an optimization problem. So basically, you have your problem you want to solve, it's very difficult, and then you just have to devise a cost function, and then hope that you can use these algorithms and try to solve the problem. But the question, of course, is this going to work? And really, there is no evidence as of today of any speed up or provable speed up that we can obtain with these variational quantum algorithms. And moreover, there are big challenges. And one of these big challenges, and arguably the biggest challenge, not the only one, but very big challenge, is that of Barren plateaus. So Barren plateaus were introduced in a seminal paper that was published in Nature Communications by the Google team. And since then, they have become like a very hot topic of research. So what is a Barren plateau, right? We have our loss function there, the expectation value of some observable, and a Barren plateau is an exponential concentration of the loss function landscape as the number of qubits increases. So basically, as we increase the number of qubits, the differences in the loss function value for different values of parameters becomes very, very small, and everything becomes exponentially concentrated, and the landscape is super flat. It's a Barren plateau. More precisely, we can say that the variance over the variational parameters of our loss function is exponentially small, or decreases exponentially with the number of qubits. So we have a Barren plateau, like the one on the left. And when this variance is at most polynomially vanishing in the number of qubits, then we don't have a Barren plateau, right? So we may have local minima. The landscape is going to be non-convex in general, but it's not going to be super flat. And more precisely, even like, why do we care about these variances? Well, or why is it a problem? We can see from Chebyshev's inequality that the probability of deviating from the loss function by a quantity epsilon is upper bounded by the variance divided by epsilon squared. So unless epsilon is so if the variance is exponentially small, unless epsilon is exponentially small, then this probability is also going to be exponentially small, right? So that means that if we want to, with overwhelming probability, if we want to distinguish things in the landscape, these differences are going to be exponentially small. So we are going to need an exponential precision in our estimation of the loss function. The problem, of course, is that we only have a finite number of such, right? And the error goes as 1 over the square root of the number of measurements. So if we want to have like an exponential precision, we need an exponential number of measurements. This is exponential time, and of course, you cannot do this for a large number of qubits.
Yeah, I have a question. So that means that if you perform an exact simulation, then you don't have the problem of Barren plateaus, I guess, because it's exact and you have infinite, basically, precision. Is that correct?
Yeah, by the way, if you want to interrupt me during the talk, please do it. I guess so far everything is well known, but please interrupt me at any moment. No, that's absolutely correct. If you have classical simulation, then increasing precision is cheap because you increase precision exponentially with the number of bits, so you can do it basically exact. The problem is, of course, whether you can actually simulate that circuit or not classically, but yeah, certainly this is a problem. This is a problem that appears on a quantum computer whenever we want to measure some observable. So, okay, yeah, this is a big problem if you have a Barren plateau. But when are we gonna have a Barren plateau, right? What are the known sources of Barren plateaus, or what they were like 3 months ago? So the first one is the expressivity of the circuit. So basically, if your circuit is very expressive in a way that I will quantify in a second, then we are gonna have a Barren plateau. In particular, if our circuit is a 2D sign over the unitary group, we'll have a Barren plateau for any initial state and any observable. And what this means is like, suppose our circuit is super expressible, it can express any possible unitary in the unitary group or in the special unitary group, and it can explore the entire group uniformly. That's what is called the Haar measure over the unitary group. And this is very expressive, right? Like intuitively, it's a good measure of expressivity because you are covering the entire unitary group, all possible unitaries. Of course, in order to explore all possible unitaries, you need a lot of depth. You need exponential depth. So you cannot be Haar random efficiently. However, there is this concept of a T design or a 2 design, which is whenever you have an ensemble of unitaries that is indistinguishable from the Haar measure, from covering the unitary group up to the second moment. So in our case, the expectation value and the variance, then yeah, that's the definition of a 2 design. So it's an ensemble that gives you the same first T moments. So here we have, if you have a 2 design, then the variance is going to be the same as if you were exploring the entire unitary group, and then this is going to cause a Barren plateau. And this is what is depicted. I cannot see the pointer on the screen, but below, here I will mention also that the reverse is not necessarily true. So if you have a 2 design over the unitary group, you have a Barren plateau, but if you don't have a 2 design, you may have a Barren plateau as well. So if you have a less expressive circuit, you can still have a Barren plateau. You may or may not have a Barren plateau. Okay. A second well-known source of Barren plateaus is the globality of the operator that we are measuring. So here let's consider circuits which have this brick layer structure where each of these blocks is locally Haar random. So it explores the SU4 group, uniformly. So we have like 2 local Haar random or 2 qubit local Haar random gates. Then it was shown, by the way, here I'm not showing references because these are well-known results in the literature, but if anyone's interested, you can ask me later and I can provide references. So here it was shown that if you have a global cost function, which means you are measuring an operator which acts non-trivially on all qubits, or at least on a number of qubits that scales with total system size. So let's say we are measuring C tensor n in the computational basis, but all qubits, then we will have a Barren plateau for any depth, for all depth. These are, of course, asymptotic results, right, as n increases. But if we have a local cost function, so we are measuring, for instance, a single qubit, then we will not have a Barren plateau for circuits which have at most log depth in the number of qubits. Yet another source of Barren plateaus is the entanglement of the initial state. So if our input state follows a volume law, we will have a Barren plateau for any observable, any circuit. So even this trivial circuit with single qubit rotations and local operators. So measuring just a single qubit, if rho is very entangled, then we're going to have a Barren plateau. The intuition here is, of course, that if rho is very entangled, it's going to be very close to the identity operator. So imagine that rho is the maximal mixed state, so it's the identity. Then the circuit acts trivially on it. We recover the identity for any set of parameters, and the variance is actually 0. So if you are close to being the identity, you are very entangled, then you are also going to have a Barren plateau. So all this is great. Well-known results that have guided circuit design for the community. But the problem is that most of them are architecture-specific analysis. So for example, the globality of the operator depended on the architecture of the circuit. You had to have these 2 local Haar random gates. So it's not necessarily obvious that this architecture-specific analysis carry over to all possible circuits. Yeah. Okay.
Do you mean that the analysis that they did to show this is tied to the architecture, or that the definition itself, what they're studying, you have to change it from architecture to architecture, so it's hard to generalize?
Yeah, no, what I mean is that the analysis the results depend on the architecture of the circuit. So for instance, here, you need to assume that you have this, two local hard random gates in order to find that the global operators actually concentrate. Here you need to have a 2 design over the unitary group, but if you don't have it, then what happens? Like, you can be very excessive, so it's not necessarily obvious how these things carry over to more general cases.
So 2 questions. The first one, it's actually from this slide. So I see in the circuit that you only measure 1 qubit. So it's this a result that only affects if you only measure a subset of qubits, or it doesn't matter, it will affect all of them. And the second question is there any intuition of, so of course, these results are mathematical results that you can prove that you obtain these variances going to 0, but is there any intuition of why is happening that? Like, do you have any, idea on that?
Yeah, thanks. So this result follows for more general circuits. Here, I just use this example because it's super inexpressive circuit. It's just single qubit rotation and it is local operator. So we are, doing all that we can in order to avoid, let's say, Barren plateaus later, but still, if rho is very entangled, you will have a Barren plateau. And of course, you will also have it for more complicated circuits as well. And regarding the second question, the intuition for me and the main problem arises with Barren plateaus because we are looking at loss functions of this form, right? So, and what are we doing here? We are taking rho, we are evolving it, so we are getting another rho, which is an operator, which lives in an exponentially large space. So this is just the inner product between two things that live in is the Hilbert-Smith's inner product between things that live in an exponentially larger space. And comparing things that live in an exponentially larger space is gonna be bad. It's gonna give you a small overlap in general. I mean, if you take some 2 points in a super big thing, then the overlap between them is gonna be super small. Or in other words, like, there are too many ways to be orthogonal to a thing if you have 2 to the n directions, and you are in one direction, then you have and a space that is 2 to the n minus 1 to be orthogonal. So this in general is going to be small. So comparing objects in large spaces is not a good idea. That's my intuition on this. Okay. Yeah, so as I was saying, all these results are very good results. They have given us a lot of understanding of potential causes of Barren plateaus, but again, this is architecture specific in most cases. And as I will show, some of these claims are actually false in general. So for instance, the globality one, we'll see that. So recently there have been efforts toward unifying and fully understanding Barren plateaus in general cases. So let's say I give you a circuit, I give you an input state and an observable. Can I predict what is going to happen for any circuit, any input state, any observable, etc.? And here, the key techniques have been related to Lie algebras and Lie groups, which are, I'll explain now what this is, but this is a very powerful framework. It's mathematical theory, was developed in the 19th century, and it's been instrumental in proving all these, unified results. So let's say we have a circuit that has the form there, so it's just the product of exponentials, right? So super general. We have some parametrized gates. These Hj are called the generators of the circuit. They are Hermitian operators, and then we have the thetas, which are the variational parameters. Then we say that the dynamical, the algebra G, is the real vector space that is spanned by the next commutators of the generators of the circuit, multiplied by I. So what does this mean? Let's say we have, let's take an example with 2 generators for simplicity, H1 and H2. Let's say they can be what, right? Then we take the commutator between them. This is going to give us a new operator, which in general will be linearly independent from H1 and H2. If it is linearly independent, we add it to the list and we iterate again and compute commutator between H1 with commutator H1, H2, and commutator H2 with H1, H2. This will give us new operators. Then we ask the question, are these linearly independent from what we had before? If so, we add them to the list, and we keep doing this until we say the algebra closes. So we cannot generate anything that is linearly independent from nested commutators. And all these nested commutators are going to be the basis for a vector space, for a real vector space. So it's a subspace of the space of anti-Hermitian operators, which in particular will be a subalgebra of the algebra associated with the group SU, where D is the dimension of the Hilbert space, so 2 to the n. And in order to get some intuition as of why should we care about all these nested commutators, then we can look at the VCH formula. So the VCH formula tells us that if we have the product of two exponentials, we can write this as a new exponential, or as an exponential of a new operator, where this operator is a linear combination of the nested commutators of these two generators. So in particular, and okay, this of course generalizes to the case where we have more than two generators. So in particular, any possible unitary in our group, so given our generators, we have a Lie group, which is the group of all possible unitaries that we can implement with this, given sufficient depth and allowing to vary the parameters. Then any unitary that my circuit will implement will be of the form E to something in the Lie algebra. So the Lie algebra characterizes the ultimate expressiveness or expressivity of our circuit. Okay, I hope this was clear because it's going to be a very important concept in what follows. In particular, the dimension of the group of unitaries that we can implement is equal to the dimension of the. Okay, so some examples. Let's say we have a circuit with single qubit rotation C and Y. We take the commutator between C and Y. We find X. So this gives us the full algebra SU2. We don't have the identity. That's what we have. Why we have the S. And okay, things acting on different qubits in different qubits commute. So we have SU2 direct sum n times. Then let's say we have this other circuit here with single C rotation, single qubit C rotation, and then 2 qubit XX rotation. So E to the I theta sigma S sigma X. This example will be important later. These are parametrized matchgate circuits, and here you can show that the dynamical algebra associated with this circuit is isomorphic to SO2N. Particular notice that we don't have an exponential in there, so the dimension of this algebra is actually quadratic in number of qubits. Finally, on the right, we have C rotation, Y rotation, XX rotation. So we can show that this is a universal circuit. So the algebra is the full. Sorry, there is a mistake there. This should be, there shouldn't be any direct sum there. This is SU2 to the end. So, this is a typo. So you see, just adding, an extra layer of single qubits can change by a lot your expressivity. You go from something which is very restricted to fully universal. This is a meme by my colleague Marcos Sereno, tries to convey the message that indeed Lie algebras are a very powerful tool to analyze variational quantum circuits, and it's the tool you should look at when studying these circuits analytically. Okay, so how all these things started? So there was this paper. It was 2 years ago, I believe, from people at Los Alamos National Lab, where they conjecture that the variance of my parameterized quantum circuit is going to be proportional to the inverse of the dimension of the Lie algebra. So if we have a circuit with a large dimension of the Lie algebra, very expressive, then this is going to vanish inversely proportional to this. So it's going to have a Barren plateau if the algebra is exponential. And very recently, like 2-3 months ago, there were 2 almost simultaneous papers. The one on the left is from the people at JP Morgan, and the one on the right is from people at different places, including some of my coworkers at Los Alamos. And they indeed proved that this conjecture was true. And before I show you the result, I will just need to introduce yet a new concept, which is also important, which is that of generalized entanglement. So what is actual entanglement? We can think of it, let's say we want to look, we have an n-qubit system, and we ask ourselves the question like, how, like we look at a single qubit and we say, how entangled is this? So a measure of that entanglement is the purity of the reduced density matrix. So it's trace of rho squared. So what are we doing? We're basically projecting our space into the single qubit algebra, so the identity x1, x, I, and c, and then we're seeing what's the component of my density matrix in these operators, and that's actually what is given as the purity. However, we need not to restrict to these particular operators, and we can generalize this concept. Say, okay, if I have an operator, rho or rho, what is the support that it has on a subspace of operators? So, for instance, in those one. And in particular, we will introduce the quantity that we call the S purity, which is a generalization of the usual purity, where what we do is we just say we have a subspace of operators S, which has some basis. Then we simply take our operator H, we project it into this subspace, and then we take the trace square of this thing, which is equal to this sum, right? This concept was introduced actually in Rolando Soma's thesis back in 2006, I think, and it just turned out to be super important for understanding Barren plateaus. Okay, so what does this result of a unified theory of Barren plateaus does? So, okay, in general, the Lie algebra of our circuit, we are going to be able to decompose it as a direct sum, because it's a subalgebra of FUD, and where the last component, okay, probably it should say with GK abelian. So we have an abelian component, and then all other so-called ideals. Never mind. Whenever rho or O is in the Lie algebra, then we have an exact for, and of course, there is an important caveat. All these results are computing variances, so we are computing the second moment, which means we are computing some integrals. We are computing these integrals over the group of unitaries that my circuit forms. So we need sufficient depth in order for my circuit to be a 2D sign over the group. So if I restrict to say I say I just have one layer or something, then this result do not apply. I need to be deep enough, which is not too deep. We just need to be a 2D sign over the group. So whenever which will be typically with polynomial depth, it will already be a 2D sign. So whenever, again, when rho or rho are in the algebra, then they were able to characterize precisely what is going to be the variance given. You give me some rho, you give me some O, you give me some circuit, and then the variance is going to have this neat formula. So let's try to understand what this formula is saying. Let's say that G is simple, which simply means that we don't have a direct sum. We just have, one component in this. Then instead of having a sum over all, these ideals, then we just have a single term, which has the same form as the one in the sum. So what this is saying is we have the G purity of rho. So how pure rho is in my algebra? What's the support or the component that rho has in the algebra of the circuit? How much component or support does my operator have in the algebra of the circuit divided by the dimension of the Lie algebra? So if dimension of the Lie algebra is very large, it's exponentially large, the circuit is super expressive, we're going to have a Barren plateau. If my initial state or my measurement operators are not aligned, so one is in the algebra, but the other has very small component in the algebra, and this purity is very small, then we are also going to have a Barren plateau. And in particular, even if the dimension of the algebra is polynomial, it may happen that, my operator is in the algebra, like in the QAOE case, for instance, or VQE typically. Yet my initial state is not well in the algebra, and then I also have a Barren plateau. So here we can see what are the sources, the actual sources of Barren plateaus. And whenever we have our algebra is a direct sum, then we just have to sum over all these components of the algebra. Okay, so this is, yes.
Can you explain the intuition of why the initial state or the operator that you are measuring like have to be in the algebra, more or less?
But they don't have to, but in many cases, in many algorithms, they are. The idea is to have these problem-inspired ansatces. So let's say you have QAOA, for instance, you want to find the ground state of a given Hamiltonian, right? H, and then what do you do in QAOA, for instance, in matchgate? You're actually using the terms in your Hamiltonian in your circuit, right? You're doing the exponentials of the things that are in your graph, for instance. The idea is, okay, if I have this problem, I want to minimize this Hamiltonian. I want to use information from this Hamiltonian, put it in my circuit, and then hope to try to that this will restrict the search space and it will be a problem-inspired answer. So that's why in all these cases, you are actually measuring something that is in the algebra. I hope that answers. Okay, yeah, so she's asking why then, even if you are in the algebra, you're measuring them, why can you then have Barren plateaus, right? The problem is that, sure, you're in the algebra, but this algebra can be super large. It can actually be universal. It can be, like you have these hardware efficient ansatses that are able to generate all possible unitaries in principle. Then your algebra is just the full algebra, let's say. So you have a very, very expressive circuit. Even if you are in the algebra. So the thing is that you can have large algebras and small algebras. So if your algebra is large, then no matter whether you have like problem-inspired things, your algebra is large, which is what typically happens, for instance, for matchgate, and which is expected because these problems are NP complete, NP hard, and whatnot. So that's basically. Okay. Mm-hmm. I see. We will see it later. Yes, I'll come back to this question later because it will be easier to understand why once I explain what comes next.
So if I understood correctly, the goal in order to have some kind of quantum advantage in quantum machine learning would be to have an algebra that is larger than what can be represented in a classical computer, but that is not universal. So you don't have Barren plateaus, right? Okay.
Yeah, and I'll come back to that as well. It's super relevant because then, well, you already see it. Like, okay, we have to restrict the dimension of the search space, but then can we use that, that reduced search space to do something classically? Okay, it may be the case. We don't know for sure, but yeah, may well be the case. Right. Okay. So this was like, in my opinion, a very big step because you still have this assumption that rho has to be in the algebra and that you need sufficient depth to have converged to a 2D sign. But okay, this is given like a full theory, let's say, or almost, based on, we still have this assumption, but like a deep understanding of what's going on in these parameterized quantum circuits. Still, of course, the problem is that we are still having this assumption that rho or O are in the algebra. And what we did in our last work, this one here, is to go beyond this assumption and generalize for any row or any O, but the assumption we have to make in this case is do the analysis for a particular architecture of circuits. But as we will see, this theory, which is still incomplete because we are still making this assumption of a particular architecture, we'll see that, in my opinion, it contains the ingredients for the final theory. I hope to convince you. Let's see. So again, we're going to focus on this work on parameterized matchgate circuits. So we're going to have single qubit zero rotation, XX 2-qubit rotations in a line, open boundary conditions. This algebra is isomorphic to SO2N, so it has a quadratic dimension, which is quadratic in the number of qubits. In particular, the algebra is spanned by those operators there. Okay, it's not super relevant now. You have just some basis of the algebra. You start, computing the nested commutator. You find this, and the key insight here is that these circuits are also called fermionic linear optics, and we can use this knowledge, and in particular, these Majorana operators, which are just Pauli operators, but they are very particular ones. They all anti-commute between themselves, and they will be key. We will be able to characterize completely the variance of these circuits using these Majorana operators. In particular, there are two important things to notice here. The first is that the space of linear operators acting on n qubits that we call B can be decomposed into 2n-1 orthogonal subspaces, which are called B of K, where each B of K is spanned by a basis of products of K distinct Majoranas. Okay, so in particular, then the dimension of each of these, we'll see they are modules, it's 2n chooses K. So it's all possible, you take all possible products of K Majoranas, and then this will give you a basis of one of each of these subspaces. And we can show that these subspaces are invariant under the action of the group, so of our unitaries, our circuit. So if we take any operator in one of these, blocks in these subspaces, we conjugate it with U and U dagger, where U and U dagger is a unitary from our circuit. We stay in the same subspace. We don't go anywhere else. So this module, then these are so-called Lie group modules, and they are invariant under the action of U and U dagger. Right? You act with U and U dagger, and you remain in the same module. And this is key. Because this allows us to, again, characterize precisely the variance for any input state, any operator in a circuit, given that our circuit is a 2D sign over the group. And the formula is kind of similar to what we had before, but it has some differences. So first, notice that here we are summing over all the modules. Okay, except first one and last one, which contain the operators that commute with the circuit. So those are trivially, but we are summing over all other modules, and we have again the same factors: the K purity of rho, the K purity of O, where now the purity is with respect to these modules. Here, I should say that one of these modules, when K is equal to 2, is the algebra itself. So the algebra is just another module. And then before we had the dimension of the algebra, now we have the dimension of the module. So we see in particular that the conjecture that the variance goes as 1 over dim of the algebra is not true in general. It's true if you are measuring in the algebra, but if you are measuring something which is in some other module, then this expressiveness quantity is replaced by this other generalized expressiveness, if you will, which is the dimension of the module you are in. And then we have some new terms, which are these C's here. These are covariance terms. And these will appear between so-called isomorphic modules. So if you have modules which are isomorphic, which means they have to have the same dimension, and you can find an isomorphism between them, respecting the algebra structure. Then you will have covariance terms, which are given by this. Here in particular, if we have the kth module and the 2n minus kth module, they are isomorphic. You can see that 2n chooses k or 2n chooses 2n minus k is the same dimension, and we can find an isomorphism, and these two are connected by the parity operator. Okay, so that was it. We had an exact formula, a variance formula for parameterized matchgate circuit, and now let's look at it in practice. So let's look at some example and some numerics and see what can we learn from that. So for instance, on the left, we have a Gaussian state. So we just have the all zero states. And we are measuring C tensor M, which as n increases is a non-local operator. So it becomes very, very global. And in particular, these operators belong to this B2M module. And what we can see here, okay, dashed lines are analytics, and then the dots are numerics. So you can see that everything matches perfectly. What we see is that when M is fixed, so for instance, M is equal to 1, so we have C1 or C2, etc., then the variance decreases polynomially with the number of qubits. But when M increases with N, then the variance is exponentially bad. And here I want you to notice that, remember this symmetry, we can have C, if C tensor 1 is the same as C tensor 2n minus 1, so we can have a super, n minus 1, so we can have a super global operator. We're measuring all qubits but 1, yet you get a polynomially vanishing Barren. So in particular, we see that you can measure global operators and get a polynomially vanishing Barren. The only thing that matters is where this operator lives, in which module you are. So once we got to understand all the structure of the modules, everything followed naturally, but at the beginning it was super unintuitive because we could just, find different operators and everything seemed kind of random. Like, okay, you take one operator, one initial state, it's going to concentrate, no, it's local. And once you understand that what matters are the modules, then you can actually understand everything. Then we have these so-called magic states, because in general, parameterized matchgate circuits, they are not classically simulable in general. It will depend on the initial state. So we have the same concept of magic as in Clifford circuits. And here we can see we have this magic state. We have, which is thought to be, classically hard. Then we have, or it was thought to be classically hard. And then we have, single qubit operator, and then the variance is polynomial. And then on the right, you see the curve is very similar to the one on the left, but conceptually is different because here we have XJ, so we have single qubit operators. These are all local operators. But again, all that matters is in which module these operators live. So in particular, you can have exponentially vanishing gradients, Barren plateaus with local operators for the same circuit. Okay. So again, the previous knowledge coming from architecture specific analysis turned out not to be true in general. So this is the picture that we have now. We have generalized, this theory beyond the assumption of the dynamical algebra. We see that the algebra is just one of all these modules. And okay, what's next? So here we were assuming that that we had parameterized matchgate circuits. So it's still not general, but one can see already what the general theory should look like because it should in particular reproduce this case. So one could envision that we are going to have, you are going to have your algebra, you are going to have all your modules, and this is what's going to matter in order to characterize or to understand or predict if we are going to have Barren plateaus. Yeah.
So from this picture, the last column on these words, generalized expressiveness, coherence, and globality, could you explain, match the concepts that you explained with all these new definitions?
Yes, so we coined these terms, just put generalized, to everything. Okay, let's start from the generalized expressiveness. So we have seen that what matters is not just how expressive your circuit is, but it's a combination of how expressive your circuit is and where your input state and observable lie. And the way I think of it is like you can also think like this row and all, they don't, they are not just given. You may have to prepare them, or you can think of them as a quantum circuit before and after your circuit, which is gonna change your expressivity. It's gonna move you to some other modules. So in that sense, we have this generalized expressiveness, which is simply the dimension of the modules where you have support. So it's a new measure of expressiveness, which goes beyond just the circuit and the algebra. It takes into account this Lie group modular structure. The general coherences, these are the covariances. So, these are cross term between different isomorphic modules. So if you have isomorphic modules here, then you can have covariances effect. And since these are off diagonal, then covariances, then generalized coherences. And generalized globality, meaning that in general, it doesn't matter if your operator is global or if it's local in the usual many-body sense, like if I act non-trivially on many qubits on a few qubits, what it matters is to which module I belong. So the globality in this case will be increasing k. So if you have the bk module, then increasing k is increasing globality. And one can think it's increasing number of products of Majorana that you have to measure. So in that sense, in the Majorana sense, if you want, it can be thought as generalized globality. Okay. Yes.
In these plots that you have shown, you have the observables and the initial state, but you have like a specific circuit that you put like in all of the plots.
So all these results are for this parameterized matchgate circuit. So this is one layer, and we are stacking layers of this, and then we are taking the variance over the parameters. Here we are taking them uniformly, and eventually here in particular we are using n squared depth. We found that in order for the points to lie precisely on the curves, we needed this depth. If you change the way you sample the parameters, then you can change this thing, but basically you need to converge to a 2D sign, so have sufficient depth for that. Here it's n squared. If it's not n squared, then you are almost there, but not. So you probably still have qualitatively the same behavior, but not quite so. It's simulation. Yeah. All this is simulation. No, here we are not taking into account, say, shot noise. This is we are sampling parameters and we are computing the loss function exactly. So yeah. Okay. So one last example about these non-intuitive behaviors that only become clear when we understand all the mathematical structure below. If let's say we have our matchgate circuit, so we have the layers of our circuit, then we're measuring the computational basis. So we are measuring C in the middle qubit. This belongs to the second module, which is the algebra, which has a polynomial dimension. So, okay, let's say your observable is in the algebra. Then you don't have a Barren plateau. Then you add a single Y gate to the circuit, single gate. Then you are effectively measuring the X operator, which belongs to this Bn module, which has an exponentially large dimension. So a single non-parameterized gate can induce a Barren plateau in your circuit. Just a single change of basis from C to X. Why? Again, not super intuitive, but it's all, algebra, groups, modules. You go from one module to the other, you are doomed. Okay, so that was almost all of it. Now for some outlook. So this is something by my friend and colleague Marco Cerezo, who has spent a lot of time thinking about this problem. It's not only been him, it's been the community, it's been putting a lot of effort into understanding this phenomenon. And I argue that this is important because we need to understand when and how Barren plateaus are going to appear, because if you have a Barren plateau, then you're not going to be able to make use of your variational quantum algorithm. So we need to understand when and how Barren plateaus are going to appear in order for us to be able to pin down where to look for quantum advantage, right? So yeah, to summarize, we are close to having a final Barren plateau theory for deep parametrized quantum circuits. And as I have said many times already today, the algebraic techniques have been instrumental in this achievement. Of course, there are still open questions, and the final theory is not here, but we can envision how it's going to be. So what happens in the shallow regime? We said that we need to be converged to a 2 design in the group. So this is still an open question, like what happens in the shallow regime? And then, as you were mentioning before, right, what are the connections between the absence of Barren plateaus and efficient classical simulability? Because we are going to be restricted to polynomially large spaces necessarily. Can we leverage that in order to do classical simulations, efficient classical simulations? This is also an open question in general. In parameterized matchgate circuits, it seems that the answer to this question is that indeed, when we have absence of Barren plateau, we have efficient classical simulability, so no quantum advantage. Is this going to be general, true in general? I argue that this is a most important question for the field. And in particular, if we want to know if Bob Stoponja is right or not, we must answer this question. So that was it. With this, I will thank my amazing co-authors, Nahuel Diaz, who is going to become a postdoc now at my group in Los Alamos, Sujay Kasi, who is extremely intelligent guy. He's just starting his PhD in Duke. Martin Laroca, postdoc there in Los Alamos, and Marco Cerezo, PI in Los Alamos. So thank you.
Thank you very much, Diego, for this masterclass on Barren plateaus theory. Well, I have actually a question regarding the last statement that you mentioned, the classical simulability of all of it. So what's your take? So do you think that we will find exceptions to all these apparently rules, that some circuits that are not trivial classically doesn't have Barren plateaus?
So yeah, I mean, that's the question. It doesn't look good. That's my take, because we know if you're in this deep regime or deep, like you're a 2 design, then we know how to use techniques which are, again, based on Lie algebraic things classically. So it turns out that the same structure allowing for the absence of Barren plateau can be used to efficient classical simulability. There is one caveat, which is for these classical methods to work based on these Lie algebra things, and you need to have a characterization of your initial state in the algebra, so, or in the module. So in particular, you may need to prepare the quantum state with some quantum circuit, then measure it a la classical shadow, let's say, not exactly, like measure it in a basis of the algebra or of the module. And then with that information, you can do the variational part classically on a quantum computer. So that's for deep circuits. For shallow circuits, we don't know, but okay, the shallower you get, the easier it should be. Then, of course, there are possible exceptions. You can, I don't know, we still don't have the final theory. So none of what I'm saying now, it's, you know, like it's written in stone. Is my intuition, is what we kind of see from these results. You can have warm stars, for instance, and then you are far from being a 2D design. If you have some knowledge that allows you to initialize properly, sure, maybe most of the landscape is bad, but then you have some previous knowledge that you can use, and then you can get away. But it doesn't look good in general.
Thank you very much. Is there any other question?
Thank you, Diego. I have a few questions. How do you, I mean, how hard is to compute the variance? What from your expression? I have no clue. You need to,
Thanks. Yeah, so the first thing you need is you need to, given your circuit, let's say your circuit architecture, you need to know what the algebra is. So, okay, if you do it, let's say you start taking nested commutators, this can take exponential time if you go to the end, but so you will rather try to rely on analytical techniques. All I can say is that circuits we've looked at, we've been able to characterize the algebra, but with the caveat that we take the parameters to be independent, which means that the generators are Pauli's, and then it's easier to compute everything. When you have correlated parameters, then it may be more difficult to actually compute the algebra. If you don't have the algebra, then you don't have anything else. So our experience is that for, you know, free parameter circuits, we've always been able to characterize the algebra. It can take a lot of effort, so it's not a trivial problem. Once you have the algebra, you also have to characterize these modules, which, okay, here we could use Majoranas, but I don't know how difficult it's going to be in general. Once you have that characterized, then everything follows, because then you do these integrals over the group, and then, so the difficult part is computing the algebra and the modules. I don't know about complexity statements. Like if you go taking nested commutators, for sure it's exponential, because if the dimension is exponential, it may take exponential time. But even with exponential time, you can, in some cases, do it analytically, and then you don't need to compute like all the commutators. And I don't know about, yeah, what's the complexity, like in complexity theoretic terms, I don't know, like, but here's the thing, like all these Lie algebra things, like these techniques are very like well established, very well known. Like we know all possible Lie algebras that can appear, all possible Lie groups. There are not so many. Then it's all about how you take like direct sums of them, but there are not many Lie algebra. And just in the mathematical part, we know all possible Lie algebras that exist and all possible Lie groups that exist, which is, for me, is mind blowing. Like we have all this knowledge. There was a paper recently characterizing if you have circuits which are translationally invariant in 1D, then they were able to compute every possible algebra that will appear from that. So it seems that in many cases we will be able to work out what's there. It may take a lot of hard work, but I don't know. I really don't know if there will be some cases in which, you know, it will be too difficult and we won't be able.
Yes, I have another question. So in classical machine learning, there is this the same problem. I mean, this is called the course of dimensionality. So you go to very large spaces, exponentially large spaces that get, I mean, is there any clear connection between these two things? Because at the end, it's the same, right? You are sampling over an exponentially large space, and guys are like very far apart, and then the distance is. But
so I don't know much about like how this appears in classical, but to me, this is exactly what's happening. You are, you know, comparing things in exponentially large spaces, and this is bad. And it doesn't work. Yeah.
yet you can train a neural network, right?
But there is a huge difference because you can have precision is not an issue in a neural network because you can increase precision exponentially with the number of bits. here the information comes from shots. So you certainly have an issue with precision. If you want to have 3 digits of precision, which is nothing compared to a classical, to a float 64 or something, you need million shots. So here precision is very bad because it goes as 1/square root of n, whereas classically, this goes back to your question. So I guess that's the way around. Here, precision is really, if we could, have like 64 floats with, million measurements, then everything would be fine. But here we cannot.
Could you relax? This is my final question, which is it's actually 2 questions. Could you relax the condition of the variability about the variance by not computing the full set of parameters? And then the other one is if you can use this information to mitigate the presence of Barren plateaus by removing these gates that move you into another.
So I'm gonna answer the second question. I forgot the first already, but absolutely, that's the idea, the whole point. Like we want to understand when Barren plateaus are gonna. Okay, now I remember when Barren plateaus are gonna appear in order to avoid them. So definitely, yes, this is actually the main point of all this thinking about Barren plateaus, thinking about Barren plateaus, etc. To avoid them and use that information. The question then is, will that render circuit classically simulable? And regarding the first question, the answer is yes, again. So changing the range of parameters, the distribution over which you sample these parameters is going to change your expressivity. So it may take more time to converge to a 2D sign. Eventually, you will converge to a 2D sign, but it may take more depth to do it. So yes, changing the parameter expressivity will change your, but I don't expect that it's gonna be key. Like in the sense that you're gonna change the depth, but it's gonna still be polynomial depth. You're gonna still be there. Maybe there is some regime. Let's say like if you need n² depth with some distribution, then with other distribution you need n depth, and then that there is a window there for classical non-simulability. That could be, but yeah, like here, for instance, we are not sampling, we are not doing high random things, and yet we get the exact variance. You are just having uniform distribution over the parameters. But yeah, like the distribution over the parameters will affect, but yeah. But also maybe you need some knowledge about it, like in which regions to look, because if you don't have any knowledge, this is supernatural, just uniformly random, because you don't really know where the parameters are, but or the good parameters are. But
any other question? If not, let's thank our speaker again. Thank you, Diego.